This is the first topic in probability, and we're going to start off with some terminologies. Firstly, the result of an experiment is called an outcome or the elementary event. A combination of these outcomes or these elementary events is what gives you an event. So an event is a combination of multiple outcomes or multiple elementary events. Then you might have heard the term random selection. Random selection is when objects are selected at random, and this is done to ensure that each object has the same chance of being selected. This makes the selection fair and unbiased. If you choose what you're selecting, then you're having a biased outcome in it. And when you're fair in selecting, any object being selected is equally likely. That means the probability of each of them being selected is the same. Suppose there is an experiment that has three possible outcomes: outcome A, outcome B, outcome C. And remember what we said about events. Events is the combination of multiple outcomes. And so suppose you do the experiment, let's say 7 times, and from that you get an outcome of A, you get an outcome of B, and you get an outcome of C. So all the possible outcomes happened in your experiment. Then that experiment or those set of events is known as being exhaustive. Then we move on to something that's known as a complement. A complement is something that's not something else. So if I say the complement of A, which is also known as A prime, when I say this, it means A is not happening. So then if you look at this example that we have of 3 possible outcomes, if you want A to happen, that's this right here. And if you want the complement of A to happen, that means A does not happen, that means you have these 2 possibilities. And in total, the probabilities will always be 1, because it goes through all the other possible outcomes apart from A. So it is A plus all outcomes but A. This will obviously go into all the possible outcomes that are there, which have a probability as a whole of 1. Then, when an experiment is repeated multiple times, each repetition is known as a trial. Then the relative frequency happens when in an experiment, which is the observed probability, in the sense, how many times did the event occur over the total number of trials that occurred. This relative frequency is not the actual probability, it's the observed probability. But we do end up using it as the actual probability at times, because we don't truly know what the actual probability of anything is. We know that by experimentation. Next is a bit of a recap, and you should be knowing how to calculate your probability. Probability is just the number of successful outcomes over the total number of outcomes. And it always has a value between 0 and 1. And the sum of probabilities is always going to be equal to 1. Because there's a 100% chance that something will happen. Relative frequency, on the other hand, is just experimental probability, meaning the number of times an outcome occurred over the number of trials in an experiment that you did. For example, if you flip a coin, then the probability of you getting head is 0.5, and the probability of you getting a tail is 0.5. But suppose you flip the coin 10 times. From that, 6 of them were head. That means the relative frequency here of you getting head is 0.6, and the relative frequency of you getting tails is 0.4. That is your probability that you got from the experiment that you did specifically. It's not what the actual probability is. Now, consider randomly selecting one student from a group of 19, where 11 are boys and 8 are girls. Selecting a particular boy, meaning one specific boy. Your probability of that is going to be 1 over 19, because you're selecting one specific boy from a group of 19, which is a mix of both boys and girls. Similarly, for selecting any particular girl, again, you are taking it from the group of 19, which is a mix of boys and girls, and you're selecting a specific girl that's there. This will be also the same for selecting any specific student. Because students are different, you picking that one specific student, doesn't matter whether it's a boy or a girl, you are still picking that one student from a group of 19, so your probability will be 1 over 19. Now yes, when you are told to select a boy, generally just a boy, then your successful outcomes are 11 because there are 11 boys over a total number of outcomes of 19 because there are 19 total students. Here you don't want to select a particular boy, you're selecting anybody that is a boy. So you get 11 over 19 as your probability. Similarly for selecting a girl, you have 8 girls in total, you don't want to select a particular girl, just any girl in general, out of a group of 19 students, so your probability will be 8 over 19. Then we go into mutually exclusive events. What exactly are they? They are the events that cannot happen at the same time. For example, you cannot get a head and a tail at the same time. You will either get a head or a tail. So getting a head and a tail are mutually exclusive events. Another mutually exclusive events are the rolling of a dice, where you cannot get more than one number at a time when rolling a dice. When you go into non-mutually exclusive events, it's stuff that can happen at the same time. For example, you want to roll a number that is even and also less than 4. Can both of these happen at the same time? Yes. When you roll 2, 2 is an even number and it is less than 4. So these events are not mutually exclusive. Another one, drawing a queen and a diamond from a normal deck of cards. Well, you have a specific card that is the queen of diamonds, where you are fulfilling the first condition and you're fulfilling the second condition. So these two are not mutually exclusive events. Yes, if they told you drawing a red and a black card, those are mutually exclusive because you can't have a red and a black card at the same time. Yeah. Now, looking at the probability of these mutually exclusive events, if you want the probability of choosing A or B, where A and B are mutually exclusive, then that will just be the probability of choosing A plus the probability of choosing B. And this gets expanded to when there are more than 2 events that are mutually exclusive. When you want to choose A and B, which means A and B at the same time, simultaneously, remember this is not possible, they cannot happen simultaneously. And so the probability of you choosing A and B will equal to the probability of you choosing A times the probability of you choosing B at the same time. That will always equal to 0 because you cannot choose them simultaneously. And in set notation, this is how they're shown. They do not have any intersection. So their intersection is 0. And the probability of A union B, which is A or B, is just equal to the probability of A plus the probability of B. Let's look at this example. The probability of rain on any particular day in a mountain village is 0.2. On how many days is rain not expected in a year of 365 days? So remember, the probability of rain is 0.2. That means the probability of no rain is 0.8. Therefore, 80% of the times we have no rain, or we can expect no rain. Therefore, 80%, which is just 0.8, times 365, which is equal to 292 days, is the number of days that there is no rain in that mountain village. And so the answer for this, on how many days is rain not expected? 292 days out of those 365 days. Next, let's look at Venn diagrams and answer the following questions. Let's say we have to shade set A. Well, we have to just shade all of A, which means all of this that's there. Just A, the circle of A. Then we're told to shade the complement of A, which remember is shown by this notation here. Then we have to shade everything that is not A. So everything should be shaded that is not A. As we can see, what I'm shading right here is everything but A. And if you see, if you add this with this, you will have shaded everything in that universal set. The universal set is the box around. So that will be the shading of the complement of A. Next, we're told to shade A union B. And what that means is shade both A and B. So we're going to shade everything that is A and B at the same time. And that is what we get. Then we're told to shade A intersection B. We have an event A intersection event B, and we're supposed to shade that intersection. What that means is you have to shade A. I'm going to use different colors for this so you realize what's going on. I've shaded A right here, and now I'm shading the whole of B. And intersection means exactly what you've learned before. Where is there blue and red both shaded? And that is going to be right in the middle here. And so that middle section is known as your intersection of A and B. Next, we are told to shade A complement intersection B. So remember what A complement was. A complement was everything that is not A. Here I've shaded everything that's not A. Now I'm supposed to shade B because that's my other event that I'm intersecting. Now when shading B with a different color, I see this. And now what the intersection is when we have shaded twice. We have shaded for our A complement and we have shaded for our B. And we see that that is right here. It's the part of B which has nothing to do with A. That's going to be our A complement intersection B. Now let's do the following examples. So we're told to shade A in the first one, and we have already done that. We have shaded A here. That's A. Then we're told to shade A complement, and that is just everything that's not A. Then we're told to shade A union B, which is both A and B, which is just this right here. Then we're told to shade A intersection B, which is when both A and B overlap, which is this here. Then we're told to shade A complement intersection B, and we just did that, and that was the part of B that has nothing to do with A, this here. And this is the opposite, the part of A that has nothing to do with B. Why? Because we are looking at not B, and we are looking at A, which is just this part right here. Now here we're given a question where we have to use Venn diagrams to calculate the probability. Here we're given that one digit is randomly selected from the digits 1 up to 9. And the three possible events are a multiple of 3 is selected, which we know is 3, 6, or 9. Then our second event is that a factor of 8 is selected, which is 1, 2, 4, and 8. And finally, a prime number is selected, which is 2, 3, 5, and 7. So let's first draw this in a Venn diagram. We have our universal set. And remember, multiple of 3. So A is 3, 6, and 9. B is 1, 2, 4, and 8. C is 2, 3, 5, and 7. Here we see that A and B do not share anything. And so A and B will be mutually exclusive. But we see that C shares something with B. And C also shares something with A. And here what we see is that 3 is shared by both A and C. And 2 is shared by both C and B. Which leaves us with 6 and 9 for A, 1, 4, and 8 for B, and 5 and 7 for C. This gives us a total of 9 numbers. We have already shown that the only pair of mutually exclusive events from the 3 is A and B because they have nothing in common. A and B, their numbers have nothing in common. We have already shown. Then we're told to find the probability of A union B. A union B is everything in A and everything in B. How many numbers are there? 1, 2, 3, 4, 5, 6, 7. So there are 7 total successful outcomes over a total of 9 possible outcomes. And that right there will be your probability, 7 over 9. Because there are 7 numbers in A union B over a total of 9 numbers. So the probability will be 7 over 9. Then we're told to find the probability of A union C. A union C, we have to count the total numbers in A and C, which is 6, 9, 3, 5, 7, and 2, which in total there are 6 numbers. Over the total possible outcomes is 9. So that's going to be our probability for B Roman 1. This is for A. And finally, B union C, we'll take the total numbers in B and C, which is 1, 4, 8, 2, 3, 5, 7, total of 7 numbers. And so our probability will be success outcomes over total outcomes. 7 over 9 will be our probability for B Roman 2. Next, we are told that in a survey, 50% of the participants own a desktop D, 60% own a laptop L, and 15% own both. So, desktop D alone has 50%, laptop L alone has 60%, and both. Therefore, D intersection L, because they have both a laptop and a desktop at the same time, that is 15%. Then what we want to do is find the percentage of participants that own neither a desktop nor a laptop. We can show that using a Venn diagram. So we have our universal set, then we have desktop, and we have a laptop. Remember, they have something that's shared because we see that D and L is 15%. Let's say this is D, this is L. In the middle here we have 0.15 showing 15%. Then the entire D is 50%. And so what will be the mutually exclusive D? That is just 50% minus 15%. That is going to be 35%. Because if 50% of people own desktops and 15% own both desktops and laptops, if you remove that 15% from here, you'll get a total of 35% of students that own only desktops. So 0.35. Same thing for laptop, we do 60 minus 15, which gives us 45%, which is just 0.45. Adding all of these together, 0.45 plus 0.15 plus 0.35 gives us 0.95. So 95% of students at least own one of the two. Therefore, the remaining 5% or 0.05 own neither a desktop nor a laptop. We solve this using your Venn diagrams. Finally, we are told to use these Venn diagrams to calculate our probability. 40 children were asked which fruits they like from apples, bananas, and cherries. Apples represented by A, bananas represented by B, and cherries represented by C. Then we are given the following pieces of data, where there are a total of 40 children. From that, 17 like apples, 24 like cherries, 8 like bananas, and 5 like none. And the distribution of liking both or all three is given within the Venn diagram. Then we are told to find the probability that a randomly selected child likes apples or bananas. Apples or bananas is looking at A union B. You don't want them to happen at the same time. It could be either or. And so what we are doing here is shading this. Apples or bananas. This gives us a total of how many students? We have 6 plus 7 plus 1 plus 3 plus 2 plus 2. 2 from here, 2 from here, 3 from here, 1 from here, 7 from here, and 6 from here. This gives a total of 21 students. So 21 students like apples or bananas. We're told to find the probability of randomly selected child. Therefore, 21 is the number of success events over the total number of events, which are 40. There are 40 students that are there. Therefore, 21 divided by 40, that is the probability that a randomly selected child likes apples or bananas.